All right, now let's talk about how to form ionic and molecular compounds. First of all, what's the difference between an ionic and a molecular compound? If you already know it, try to say it before me saying it. So, an ionic compound is one that involves a metal. Now, where are our metals on the periodic table? Let me grab a. Aha. Okay, we have a Sharpie. So, on our periodic table, which I have here, which I'm going to write down here because I can't write anywhere else, there is a division line that shows us where the metals are split off from the nonmetals, and we call those the semimetals or metalloids, but semimetals is the newer term. So boron, silicon, germanium, I believe that's arsenic. Yeah, it is. Don't know that one. Tellurium, polonium, don't know that one. And then we ignore the ones beneath it. So these here are our metalloids. These are our division line. Everything to the left of them, including aluminum here, is all metals except for hydrogen, which is a nonmetal because it's a gas. I think it just, you can figure it out just by knowing that hydrogen is a gas. And these ones here are all nonmetals. These ones here, including helium, are nonmetals. Now, sometimes metalloids can be treated as nonmetals. So that's how you know that, except you kind of just have to remember what those ones there are. Now I'm going to have this here and I'm going to refer to it every once in a while. So now we have each of these ionic or molecular compounds written here, and we're going to try to figure out what they are based on just their name, literally just their name. So also just because I don't have all of the ions memorized, which you should, um, I'm going to keep the list of ions right here. Now, first we have sodium chloride. Is it ionic or molecular? It is ionic because sodium is a metal. It begins with a metal. Now, ionic compounds always consist of one cation and one anion, or multiple of each one individual. So, and what I mean by that is you would have like two of the same cation and then two of the same anion or something like that. So basically what that means is you have one thing that is giving you a positive charge and one thing that is giving you a negative charge. So the positive charge is almost always, well, actually always the metal, and the anion is always is always the nonmetal or metalloid if there is one. So how do you figure out the charges of certain things? The periodic table literally tells us the charges if you didn't know that, with the exception of some things. So the periodic table, when dealing with solid elements, tells us the charges of everything that is not a transition metal, which are in columns 3 through 12, the ones that are the lowest. So columns 1, 2, 13, 14, 15, 16, 17, and 18 do tell us the charges just based on where they are in the periodic table. So now, before I begin, I want to just say that in an atom, electrons want to be filled up in their proper spheres. So the beginning sphere only consists of 2 electrons, and then this would be your nucleus in here. The next one consists of 8 electrons, and then you go so on, where I believe the next one is 12 electrons. No, it is not. It is probably 8 electron shells numbers. Yeah, you go 2, 8, 8. So then you get another 8. And then for the most part, that's all we're really going to try to deal with. I believe that it continues in this 8, 8, 8, 8, 8 pattern. So what happens is, unless we're dealing with hydrogen or helium, which we're not in most of these cases, you want to fill up to 8. All atoms want to tend towards being the noble gases, which are on this side, which have completely full electron shells. Now, whether that means that the atom has to give up or take electrons from other molecules or share them is up to them to do when they pair with other molecules or other atoms. Now, if we're always trying to fill up to 8, what does that have to do with charges? So our first column here has a positive 1 charge. Our second column has a positive 2. Third column, a positive 3. And then now, because we're moving into metalloids and nonmetals, and I'm saying it's a positive 3 if we're going aluminum down. Now, boron would also technically be a positive 3, but it works kind of weird because it's like, in this case, just a little on the off side. Now you get into nonmetals, you get a minus 4, then you start going down from minuses. So minus 3, minus 2, minus 1, and then 0. You'll never see these really in bonds with other molecules because they are already content with being where they are. They don't need any other molecules. So that means everything in the column where nitrogen is has a minus 3. Everything, well, except for bismuth way down here, because that's a metal. Now everything in this column 2 here has a plus 2. Everything in this one here has a plus 1, even hydrogen, because there's only 1 electron there. And that's why you skip over pretty much everything from hydrogen to helium, because it describes electron shells. In the first shell, there's only 2. I just erased the drawing. In the first shell, there's only 2, so that's why you go straight from 1 to 2, and then you go 8, then you go 8, and then here you go 8 minus all of the other things. Each row, if you didn't know, is a new electron shell. Now let's actually solve for the thing, because that's how you read the thing. And then that doesn't even count all the different kinds of ions. Notice how here there's all of the alone ones, which we don't need to memorize because the periodic table tells us everything. So these ones here are ones that we do have to memorize, the ones that aren't alone, like permanganate, zinc, or actually zinc is a transition metal, so you do have to memorize that one. Peroxide, chlorate, chlorite, phosphate, phosphite. Those are the ones that are weird, but just know if it ends in "ide" or basically "ide" or is the name of the actual element, it is just the element. The rest of them are eights or ites, and that's how you know that those are ones that you have to memorize. The eights will always have more oxygens. The ites will always have less oxygens, because all of the eights and ites have oxygens by them. And they will always, if they're involving the same base element, like for this instance, it's phosphate versus phosphite, where they both involve a phosphorus, they have the same charge, no matter the amount of oxygens. So now that we've differentiated how that works, and then of course you would have to memorize all of the other ones like phosphate, phosphite, carbonate, hydroxide, ammonium, all that nonsense, then you can start doing these. But I'm going to refer to this because I'm still not along there yet in memorization. So now sodium chloride, let's begin. This is probably the easiest one that we're going to have to deal with. Where's sodium on the periodic table? Right there, Na. It's easy to memorize these, or it's much easier for you if you memorize all these. So this here is sodium, so that means it has a charge of +1 since it's in the first column. We're looking for chloride, because it ends in ide, so it's just chlorine. So chloride, that is a -1. So those would pair nicely because we always need there to be a non-positive or non-negative charge. So the charges must cancel out no matter the cost, whether that mean that you have to add more atoms to equal 0. So we have a +1 and a -1. So we are content with just having 1 Na, 1 Cl. I'm going to write my L's not weird. This isn't math, this is chemistry. So that is the written form of the ionic compound sodium chloride, if you don't know, table salt. Now, magnesium iodide, we get a little bit weirder. So iodide, first of all, we don't have to go to our weird ions list because it ends in ide. we have magnesium here. We know that that's an ionic compound because because it starts with magnesium, which is a metal. Now magnesium is a +2. Iodide is a -1. So that means we have to have two iodines to satisfy the +2. So we go Mg I2. And representing more than one atom in any compound, you write it in the subscript. You don't write it like, I would hope you would know this. You don't write it like this or something weird like that, or you don't write it like this either. No, those will get you marked way off because that should be completely common knowledge. Now we have a little Roman numeral nonsense, lead chloride. So first of all, let's just note that lead is down here, way down here. Now, normally you would be able to say, oh, it's in this column, so it must be this. But no, you actually can't do that because lead has more than one different kind of electron, hence the Roman numeral. You must specify Roman numeral when talking about different metals that have, and typically they'd be transition metals that have different amounts of electrons in their shells at any given time. They can have different charges. Like here, lead is lead 2 versus lead 4, charge 2, charge 4. If you can't tell, the Roman numeral just says how many plus it is. So this is lead 4, which means we're dealing with a +4. And then chloride, which is ide, so it's just chlorine, is a -1, like we know from earlier, which means we need to have 4 chlorine atoms to satisfy the one lead 4 atom. So we're going to have PbCl4. Okay, now we have calcium phosphate. So now we're dealing with a phosphate. It's not a phosphide or something like that. So we're dealing with a phosphate, which means we need to reference our ions list, or in a better case, our brain. So phosphate deals with a -3. Calcium deals with a +2. So the least common multiple between 3 and 2 is 6. So the calcium would be multiplied by 3. So we would have calcium and then the 3. And then the phosphate, which looks like this, PO3, would be 2. So you would put a parenthesis, PO3, 2. And that's how you write there's more than one of each of these. You cannot just write this, calcium 3, PO3, 2, because then that looks like 32 oxygens. You need to specify that you mean 2 of everything here. And you also can't just do this, because then it looks like you're involving algebra in this thing and then there's 6 oxygens. That's just not how you do it. So this is calcium phosphate. Now we get new things. So these are the molecular compounds. Molecular compounds do not start with a metal. They start with a metalloid or semimetal or nonmetal, most often nonmetal. So now let's talk about how these work. So these ones are entirely based off of prefixes. So if you don't know, and what I mean by prefix is the beginning of the word, they will always specify what it is with the base and then how many with the prefix. So we have dihydrogen. If you don't know the prefixes 1 through 10, you should memorize them because they are very useful. It goes mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, so you just need to know it. You don't need to know it super well, especially when you start getting up to the bigger numbers. You won't see really much past hepta very often. So we have dihydrogen monoxide. So we have di, 2, hydrogen, monoxide ends in ide. So there are only just oxygens being talked about here. Mon as in mono as in 1. So we're having 2 hydrogens, 1 oxygen. Hey, doesn't that look familiar? It's water. Okay. Carbon dioxide, same deal. This is ending in ide, so we're only dealing with oxygens. carbon doesn't have a prefix, which means that there's only one of them. So we go 1C, dioxide, 2 oxygen, CO2. That's what's destroying our planet right now. No. Okay, now we have arsenic pentafluoride. First of all, extremely dangerous gas. Do not breathe that in. Will kill you instantly, probably. So, because things with arsenic are incredibly dangerous and things with fluoride tend to be pretty dangerous. So, putting the two together is incredibly dangerous. So, arsenic, pentafluoride, arsenic does not have a prefix, so there's only going to be one of them. And then pentafluoride, penta means five, so we're going to have five fluoride individual elements of fluoride because it ends in "ide," not "ite" or "ate." So we're going to have arsenic Fl5, and that is our molecular compounds. And that is how you do all of those. Molecular compounds are a lot more similar, or a lot more simple than ionic compounds.